Problem session. Section 7-1. To begin with, let me recall from a theorem 7-3 tells us that if G is a primitive root modulo M, then the reduced residue system modulo M can be written as G squared and up to G to the power phi of M. So powers of a primitive root give us a reduced residue system. Of course, there is a right amount of them. There are exactly phi of M elements in a reduced residue system. We proved they are all distinct modulo M. They are all relatively prime to M. In this connection, in the exercises, they introduce the notion of index. So for a number A, relatively prime to M, so for A in reduced residue system modulo M, they introduce index and G, a primitive root, they introduce index GA is a power to raise G in order to obtain A modulo M. So that means that G raised to the power index GA is congruent to A modulo M. Roughly, we take what is the meaning of this index. We take an element from reduced residue system. This is one of them. This is one among them. This is a power of G. This power is called index A to the base G, index of A to the base G. That notion allows us to solve several exercises. Here I will not solve the first exercise. It is solved in the back of the book. And second exercise is also solved, but I will just copy the solution from the back of the book. So they ask in this second exercise, they ask to construct a table of indices of all integers for m is 17 and g 3. So we have m 17 and g equals 3 is a primitive root. Oh, we do not need now to prove that. We'll automatically prove it while constructing the table of indices. Also, we know primitive roots do not always exist, but 17 is a prime, and we already know from the next section that there exists a primitive root modulo 17. We even can calculate how many of them are there. 3 is one of them. So let me copy the table from the book. So we have A and index G A. When A is 1, the index is 16. What does it mean? This means that 3 to the 16 is congruent to 1 mod 17. This is exactly what this means, that the index of 1 base 3 is 16. So, by the way, is the index really defined as a number? Let me make a remark. Index is not defined uniquely as a number. So, remark. Index of A to the base G is defined modulo phi of m. So it is not defined in fact as a number, but as an element of complete residue system modulo phi of m. What we speak about here is any representative of a residue class modulo phi of m. So 3 to the 16 is 1 modulo 17, but 3 to the 32 is also 1 modulo 17. So 16, by the way, is phi of 17. Now, how to construct such a table that first entry is clear, how to proceed. Well, in fact, it is easier to take just powers of 3, say 3 squared is 9, and this is 9 modulo 17. So we will have somewhere here a to be 9, and the index is 2. 3 cubed is 27, which is 10 modulo 17, and we somewhere will have 10 and 3, but this 3 corresponds to this 10. Oh, if I construct the table this way, it will be difficult to write it correctly, so I hope the pattern is clear, and it is clear how to produce the table. Now I will just copy it from the book to 14, 3, 1. This entry is very clear. 3 to the 1, 3, 4, 12, 5, 5. Let me erase these entries and continue, otherwise 5, 5, 6, 15, 7, 11, 8, 10, 9, 2, 10, 3, the entries we produced here. One can continue 3 to the 4. You will not calculate really 3 to the 4. You will just multiply this 10 by 3. This is 30. And reduce 30 modulo 17. This is 13. 13. 4 is going to be another entry. This way you produce it, and after that arrange in natural order of A's. So you produce it in the order of indices, and after that rearranged in the order of A's. 11, 7. 12, 13. I'll put this entry in place. 13, 4, 14, 9, 15, 6, and 16, 8. The table is copied from the book, and I hope you understood how to produce it. Now, with the help of this table, we can solve further problems. Therefore, I copy the table here. Problem 3. We want to solve a congruence. 9x is congruent to 11. Mod 17. So we want to solve this congruence for x. You may, of course, solve this congruence in the old-fashioned way. You find the inverse of 9 modulo 17, multiply both parts of the congruence by the inverse of 9, and find x. We try to do it differently. Now, this alternative method has its advantages. Now look, 9, what is 9? 9 is 3 squared. So we can write that 3 squared x, we want it to be congruent to 11. What is 11? 3 to the 7. Modulo 17. And now we immediately find that x is congruent to 3 to the 5. Three to the 5, now I have to search for this 5 here, and this corresponds to this 5 there. 3 to the power 5 is congruent to 5 modulo 17. So the answer is 5 modulo 17. So we use, instead of using the full multiplication table, modulo 17, to find the inverse of 9, and after that to multiply this inverse by 11, we use the fact that all of them are relatively prime to 17, 9 and 11, and therefore can be presented modulo 17 as powers of the primitive root, any primitive root. 3 has been chosen arbitrarily, but that helps. So that in this way, we substitute relatively difficult operations of multiplication and especially division. We have to divide 11 by 9 modulo 17. By addition and subtraction, we now do not need to divide 11 by 9. We simply need to subtract 2 from 7. We produce the answer. Next, congruence to solve example 4, exercise 4. Solve the congruence for y squared is congruent to 1 modulo 17. We again rewrite 4 and 1 as powers of our primitive root, which is 3. The choice of primitive root, let me reiterate on that, is arbitrary. You may work similarly not with 3 but with any other primitive root modulo 17 to solve these kind of congruences modulo 17. So 4 is 3 to the 12. We write it 3 to the 12 y squared is congruent to 1. 1 is congruent to 3 to the 16. Again, instead of dividing by 4 modulo 17, we simply subtract 12 from 16. Y squared should be congruent to 16 minus 12, 3 to the 4. I would not recommend at that moment take square root. Instead, we are solving congruence, not really equation. So it's not equal but congruent. What is written here? It is written, we can rewrite it as 17, it's same thing as 17 divides y squared minus 3 to the 4. At the same time, we know that y squared minus 3 to the 4 is equal to y minus 3 squared, y plus 3 squared, plus 3 squared. We want to make minus in fact. So plus 9 as congruent to negative 8 mod 17. 3 squared is 9, and this is same thing as negative 8 mod 17. Because 9 plus 8 is 17. So this is same thing as, now it's not equal but congruent, y squared minus 9, or let it be this way, let us write it uniformly, and y squared minus 8. Let me write 8 also as a power of our primitive root. Who is 8? 8 is 3 to the 10. Three to the 10 is 8 as the member of reduced residue system. This is the index. 3 to the 10 is 8 modulo 17. So we write it y squared minus 8 plus 9 is the same thing as minus 8. Minus 8 is minus 3 to the 10. Oh, sorry. I wanted to write that as 3 squared and that as 3 to the 10. Oh, and of course, I'm very sorry. It's not squared already. It was squared here, but now these are not squared, just y's. Okay, so thus we rewrite the congruence we want to solve as 17 divides this difference, and this difference is modulo 17 same thing as this product. So 17 divides the product of two numbers, y minus 3 squared. Sorry, I did not need the squares. I'm sorry. It suffices to have indeed 9 and 8. I don't want to go further. I don't want to take square roots again. So 9, 8. So 17, so we rewrote this congruence as 17 divides the difference factors. And we wrote the factor as y minus 9, y plus 9, 9 is negative 8, the same thing as y minus 8. So altogether 17 divides this product. Here we go. 17 divides the product. 17 is a prime. Prime divides the product of two numbers. Means the prime must divide one of them. Say by the fundamental theorem of arithmetic. Thus, we got 17 divides y minus 9, or 17 divides y minus 8. This is one solution. What is written is y is congruent to 9 mod 17. And another solution is y is congruent to 8 modulo 17. This is the answer to this congruence, quadratic congruence. Turns out it has two solutions. Another next exercise we want to do 5. We want to solve the congruence 12x squared is congruent to 7 mod 17. We do same thing again. 12. Let us go here to the 12 is 3 to the 13. Table of indices helps us to solve these problems easily. So 12 is 3 to the 13, and 7, which we will need, is 3 to the 11. So we can rewrite it as 3 to the 13 x squared is congruent to 3 to the 11 modulo 17. Now I want to say that x squared is 3 to the negative 2. I don't want to say that. I don't want to calculate negative powers. That is why I said that index is not really defined. It is defined modulo phi of m. It is not really a number, but an element of a complete residue system modulo phi of m. So instead of this 11, we easily can write 11 plus 16. 3 to the 16 is 1 modulo 17. So 3 to the 11 plus 16, which is 27, this is 3 to the 11 times 3 to the 16, and 3 to the 16 is congruent to 1, so this is congruent to 3 to the 11 modulo 17. So we rewrite it this way: 3 to the 13 x squared is congruent to 3 to the 27. This way we avoid negative powers, which possibly are not convenient. We can write it as x squared. Now is congruent to 3 to the power 27 minus 13, which is 14. We again now can do same thing with this as in the previous problem. That boils down to 17 divides the product of x minus 3 to the 7 x plus 3 to the 7. 3 to the 7, what is that? Now, let us look. 3 to the 7 is 11 modulo 17. So we can rewrite it as 17 divides x minus 11. Well, let me do it this time differently. I will write x plus 11. 11 comes from here. 3 to the 7 is 11 modulo 17 from our table of indices. And now we can, one solution is pretty easy. Another solution is going to be x is congruent to negative 11 modulo 17, which is absolutely correct, but a little bit aesthetically irritating. Negative 11 is same thing as 6. This is congruent to 6. Indeed, 6 plus 11 is 17, so negative 11 is congruent to 6 modulo 17. Thus, we can write the answer here. X congruent to 11 and x congruent to 6. Solved. To conclude this series of problems, it is possible to address these problems and to solve them using multiplication table modulo 17. It is not very difficult, it is just more difficult computationally than what we actually did. We substituted multiplication with addition and division modulo 17, which is doable but unpleasant. We substituted it with subtraction modulo 16, which is much easier to perform. Next problem, problem 6 from the book. They want us to find all primitive roots modulo several numbers. I will not do all of them. Let me choose, say, 11. So primitive roots modulo 11. We want to find all of them. We can tell in advance how many are there. So theorem 7-5 tells us if there is at least one primitive root, there are so many. There is at least one, we know that from the next section. 11 is a prime. There is a primitive root modulo any prime. So theorem 7-5 then tells us that there are from theorem 7-5 we conclude that there are phi of phi of 11, which is phi of a prime is prime minus 1. Phi of 10. Phi of 10 is phi of 2 times phi of 5. We remember that phi is a multiplicative function. Phi of 2 is 1, phi of 5 is 4. So we conclude there are 4 of them. And we want to find them all. Oh, these primitive roots are some members of reduced residue system. The reduced residue system is easy to write down. So we have the reduced residue system. Let me write it. Modulo 11. All integers smaller than 11 relatively prime to 11. Well, these are all integers smaller than 11. All positive integers smaller than 11. 1, 2, 3, 4, 5, 6, 7, 8, 9. We know for sure that 1 and 10 are not primitive roots. What is a primitive root? So, primitive root, so let me record what we are searching for. So, for a primitive root, phi of 11, which is 10, should be the smallest positive integer h such that j to the h is congruent to 1 modulo 11. In other words, for a primitive root g, let me say that this is for a primitive root g. Since phi of 11 is 10, this should be the smallest positive integer such that this congruence holds. In other words, the length of a cycle should be exactly 10. All these powers should be covered with the primitive root. 1 taken to the power 1 is 1, and that's it. The smallest positive integer is 1, not 10. So 1 is not a primitive root. 10 is also not a primitive root. The integer minus 1 has a cycle length of 2 and most probably is not a primitive root. We need a cycle length of 10. So what can we do besides that? It is really difficult to rule out others. So let us better just give it a try. Try to just check anyone. If it is not a primitive root, we will rule it out as we ruled out 1 and 10. If it is a primitive root, that will also help us. Ruling out something which is not a primitive root along with its orbit also helps. So in this case, we are lucky. Well, not depends on what does it mean to be lucky. Both ways are good. Both outcomes of an experiment are good. So we want to know if all of them, or if the length of the cycle is 10. So 2, 4, and 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16 modulo 11. 5 times 2, 10, times 2, 20 modulo 11, 9, times 2, 18 modulo 11, 7, times 2, 14 modulo 11, 3, times 2, 6, times 2, 12 modulo 11, 1. How many of them are there? So after that, next one is going to be times 2 is 2, and the cycle repeats. How many of them are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All 10 of them are here. So what we found, there are 10 of them. Thus, 2 is a primitive root. How do we proceed after that? We found one primitive root out of 4, and it is not a good idea to continue trial and error. Instead, we'll use corollary 7-1, I believe, yes. Corollary from corollary 7-1. We know that if G is a primitive root, G to the R is primitive root. Now 2 is a primitive root here. 2 to the R is a primitive root. Modulo 17 if and only if the greatest common divisor of Rn, not 17, but phi of 17, no, modulo 11, sorry, the greatest common divisor of R and not 11, but phi of 11, which is 10. Here, 10. This 10 is phi of 11. Is 1. So these are 1, which will give us 2 to the 1 is 2. 2 is not. 2 is not relatively prime to 10. 3 is relatively prime to 10. 4 is not relatively prime to 10. Both are divisible by 2. 5 is not relatively prime to 10. Both are divisible by 5. 6 is not relatively prime to 10. Both are divisible by 2. 7 is relatively prime to 10. 8 is not relatively prime to 10. Both are divisible by 2, but 9 is. So we found, this way we found 4 values of R as expected for 4 primitive roots. So primitive roots are two to the 1, 2 to the 3, 2 to the 7, and 2 to the 9. It is probably better to find who are them here. This is 2 to the 1 is congruent to 2 mod 11. 2 to the 3 is 8 mod 11. 2 to the 7. How to calculate? 2 to the 6 is 8 times 8, 64. It's 9 modulo 11. Times 2, 18, 7 modulo 11. And 2 to the 9 7 times 4 to the 2. That's 28 modulo 11 is 6. That's it. This is the answer. Two, 6, 7, 8. We found all primitive roots modulo 11. What? Now we know the answer. So we might address the question, what if we were not that lucky? From the first attempt, we found a primitive root. If not, what do we do then? assume that we started with who is not a primitive root. 3. Not with 2. What happens then? How would they proceed our trial and error? We took 3 instead of 2 and tried to find out whether it is or it is not a primitive root. 3, 9, 3 by 3, 9. 9 times 3, 27, modulo 11, 5. 5 times 3, 15, modulo 11, 4. 4 times 3, 12, modulo 11, 1, and after that, the cycle repeats itself. The length of this cycle is 5, not 10, as it was in the case of 2. So, if we started with 3, we would conclude that 3 is not a primitive root. So 3 to the 5, this is 3, 3 to the 1, 2, 3, 4, 5, is congruent to 1 modulo 11. So 3 is not a primitive root. Modulo 11. Three is not a primitive root. How do we proceed? Do we want to pass to the next try? Or we can squeeze a little bit more information out of this calculation. Yes, we can. Look, besides the knowledge that 3 is not a primitive root, we can find out something about 9, 5, and 4. Indeed, this is a power of 3. So, at most, fifth power of 9 is going to be 1 modulo 11. So, all these are also not primitive roots immediately. They are powers of something which is not a primitive root. So, as an example, let me show 5 is congruent, as we found, to 3 to the 3 mod 11. So 5 to the 5 is congruent to 3 to the 3 to the 5, which is same thing as 3 to the 5 to the 3. Both are 3 to the 15, but this we know is 1 modulo 11 taken to the power 3 is still 1 modulo 11. So if G is not a primitive root. Its powers also are not primitive root. This short cycle cannot touch a primitive root. Thus, we can conclude if we have made a wrong choice, we still can conclude that not only 3 is out, but also 9, 5, and 4 are out. What we are left with are 4 suspects: 2, 6, 7, 8. All others are out. But we know that there are exactly 4 primitive roots. That's it. We are done. Those suspects, all 4 of them, must be primitive roots. So if we have chosen something which is not a primitive root for the first try, we may be even luckier. We've managed to rule out enough candidates so that the rest must be primitive roots. We know there must be 4 of them. There are only 4 suspects. So all of them are primitive roots. Thus, in both cases, we are kind of lucky. With this choice, in this particular example, with the choice of 3, we are even luckier. We got away with a smaller amount of calculations. They also ask some other moduli to find primitive roots. I will not do all of them. They're kind of similar, except 15 I did in the lecture as an example. There are no primitive roots. Module 15, you may find it in the lecture. So this is about problem 6. The last one in this problem set is problem 7. So suppose G is a primitive root modulo P, P prime. And P is a prime. Suppose M divides P minus 1. And we also suppose that M is, of course, small positive integer, which is not P minus 1, is bigger than 1, not 1, and not P minus 1 itself. And the question is, how many solutions under these assumptions the congruence as the congruence. the congruence as x to the m minus g is congruent to 0 modulo p. So we can rewrite this congruence as x to the m is congruent to g modulo p I started to solve it, and I would raise both of them if, put it differently, let x be a solution. I want to prove that the answer here is the congruence has no solutions. And what I want to do, I want to prove it. So I assume that x is a solution. I want to prove this answer. Assume we have a solution. I want to find the contradiction. If x is a solution, then we rewrite the congruence as x to the m is congruent to g modulo p. Then we raise both to the power p minus 1 divided by m. Is congruent to g to this power. What I want to say is that this congruence is impossible. That cannot happen because x to the m raised to the power p minus 1 divided by m is equal to x to the power p minus 1. And that can be congruent either to 1 f p does not divide x by Euler, or by 0 if p divides x. Then x is 0 modulo p, and raised to some power it is still divisible by p, so still 0 modulo p. At the same time, since p minus 1 divided by m is smaller than p minus 1, which is phi of p. And G is going to be a primitive root modulo P. So the smallest power to raise G to get 1 is phi of P. G to the P minus 1 divided by M cannot be congruent to 1 modulo P because it is a primitive root and P minus 1 over M is smaller than the smallest power to raise G to get 1. At the same time, G is a primitive root, so G is relatively prime to P, not divisible by P, so G to the P minus 1 divided by M also cannot be 0 modulo P. So this is either 1 or 0 modulo P, while this is something but not 0 and not 1 modulo P. Thus, the congruence cannot happen, and the answer, this congruence cannot happen, and our answer that this congruence has no solutions is proved. That is all about section 7-1. Thank you for listening.